Hi, I'm Cameron Bahar, CTO of Huawei Storage. Thanks for taking the time to join us today as we discuss some of the most important features of all-flash arrays. Two prominent features of all-flash arrays are inline deduplication and compression. These features, when combined, help save space and reduce write amplification. So what makes these features so important to all-flash arrays? Storage systems, as you know, are quickly transitioning from using magnetic disks to flash media. The adoption of all-flash arrays in the market today continues to accelerate at a rapid pace. Although the raw performance of flash is quite high, the medium itself is limited by the amount of wear it can handle and take from rewrites. As a result, the amount of wear on flash needs to be carefully considered when designing all-flash SSD systems. Deduplication and compression solve both of these problems simultaneously. Deduplication reduces the number of writes and the volume of data being written. Compression, on the other hand, reduces the volume as well. Combined, these two technologies provide the best defense against wear while improving system-wide utilization and extending the service life of SSDs and therefore the entire system. There are two common approaches to deduplication in our industry. The first approach is called a strong hash. The strong hash uses SHA-1 or SHA-2 to fingerprint individual blocks. If the fingerprints on two blocks is a match, the system will consider the blocks to have identical content. Although the probability of conflict is low in strong hash algorithms, there is still a probability that it will produce collisions. Google, for example, has recently shown that there are issues with collisions using the SHA-1 algorithm. The second approach is called a weak hash. The weak hash, the deduplication using a weak hash approach makes use of a weak hash for fingerprints, but in addition performs a byte-by-byte comparison of the two data blocks in the unlikely event of a hit. The use of the weak hash algorithm along with the byte-by-byte comparison eliminates the possibility of returning incorrect data due to weak hash collisions. So the weak hash has an extra item which we call a byte compare. Okay? Huawei Dorado V3 products use this second technique to implement deduplication. So how does inline dedup and compression actually work in the Dorado V3 system? Let's follow the path of an 8K write through the system as an example. When a block is first written, it's an 8K block, right? It's written to the cache. It's a persistent cache, right? And the write is immediately acknowledged. This allows the system to have low latency writes. When the data is stored in the cache and batched to a sufficient degree, then this data is flushed to what we call an SSD pool, which is a collection of SSD drives. It is on the path from the cache to the SSD pool that dedup and compression take place. So there's several steps in this process. The first step is, for dedup and compression, is that the fingerprint of each block is calculated using a weak hash algorithm. In the second step, global dedup takes place, which ensures that data across all LUNs and controllers in the system is deduped. And in step 3, we actually do a hashing scheme to decide which controller should receive a particular block in the system. So in step 4, when we're actually looking at these data blocks before they're actually flushed to the SSD pool, is we look at this fingerprint index of the block and see if it exists in the fingerprint index. There is an index called the fingerprint index. Now, for the corresponding controller, of course. If the data is read for that fingerprint, we'll go through a byte-by-byte comparison. If the comparison produces a match, that means the fingerprint index matched and the byte-by-byte comparison showed the same data block. That means we have the data already in the pool. So all we do is increment the reference count on the block and mark the block for deletion, and the reference count, as I mentioned, is incremented in the system. If, however, the fingerprint doesn't exist in the system, or if it exists and the byte-by-byte comparison is different, the data will be prepared to be written to the SSD pool. It is during step 5, at this point where we're getting ready to flush the data to the SSD pool on a new block, that compression is done in line on that data. Dorado uses the popular LZ4 compression algorithm, which has been vetted by many vendors over a long period of time, so quality and reliability of these algorithms are great. And step 6, the final step in the write process, is that the write is compressed and data is written to the SSD pool, as I mentioned, and the corresponding metadata is also stored and updated. This completes the path of a complete 8K write into our system. So let's talk about performance a little bit. As we know, all flash arrays are good at random IOPS and high IOPS because of the media enabling these features. But predictable performance and low latency are the hallmarks of a good all-flash array. Dorado V3 achieves a 0.5 millisecond predictable latency across low to high IOPS range. Huawei also guarantees a 3:1 data reduction ratio in all its Dorado V3 arrays, effectively lowering TCO for all customers. These rock-solid arrays are being used across multiple use cases such as VSI, VDI, OLTP, and a host of others. So to sum it up, enabling inline dedupe and compression on Huawei Dorado V3 reduces wear on flash media and extends the service life, all without degradation in performance. Stability and predictable performance are the hallmarks of our all-flash arrays. Thank you very much.